Good morning, Matt. Thank you. All right, good morning, everyone. We're pleased to have this week for the IQS seminar, Étienne Jussiau, coming to us from Rochester remotely. Étienne is French. He was born in Dijon, if my memory is correct, and then he did his studies in Grenoble, working with Rob Whitney on the physics of mesoscopic transport and charge and heat transport, and has been working with me as a postdoc at the University of Rochester for the past couple of years, and we've done a lot of great research together. And so the title of his talk is Thermoelectric Transport Across Single-Level Quantum Dots.
Yep. So yeah, thank you very much for the introduction, and thank you for giving me the opportunity to talk in this IQS seminar. So today I will be talking about thermoelectric transport across single-level quantum dots, and a lot of these topics will involve ideas revolving around thermodynamics. And usually what first come to mind when you discuss about thermodynamics are the kind of pictures I have down here. So when you imagine a heat engine that would absorb heat to give work, you imagine a train that would, where you heat coal, and this gives you some mechanical work that helps you move your train. Or alternatively, you can have a refrigerator where within your refrigerator you have this circuit where a fluid undergoes various compression, and that allows you to transfer heat from a very cold reservoir to a slightly less cold one. But work does not necessarily need to be mechanical. And so even though it has been discovered in the 19th century, thermoelectricity has only regained interest quite recently in the 90s. And so two prominent effects in thermoelectricity is the Seebeck and the Peltier effect. So basically the Seebeck effect is when you realize that you heat, you apply different temperatures at 2 points in the circuit, you will have a temperature difference that will grow between those 2 points, and that can give rise to an electric current. And the Peltier effect is the opposite effect, where you drive an electric current, and this is accompanied by a heat current. And of course, the reason for these effects to exist is the fact that electrons do not only carry electric current, they also carry heat current, because they have certain energy that they may displace from one place to another. And one great feature of thermoelectric generators is the fact that they are very reliable. This is because they don't contain any moving parts. And so they are used in some very sensitive contexts. So here I give the example of space exploration with the Curiosity rover, which is on Mars, or the Voyager space probe. And both of these technical prowess feature thermoelectric generators. And so nowadays, you can even design so-called quantum thermoelectrics, where the system which is responsible for the conversion of heat into electrical power is a very small system for which quantum mechanics must be taken into account. So here I give some examples of some experimental works where people have been using some molecules in between two gold tips to perform heat-to-work conversion. And you can even have these single atom junctions where you just have a single atom connecting the two tips. And so that, as I said, quantum mechanics must be taken into account when you study this kind of system. So it's the first interesting thing to understand the interactions, the interplay between quantum mechanics and thermoelectricity, but also it is believed that this kind of system will be very important in the future of energetics. One of the reasons for that is, since they are a very small system, quite simple system. You have a few number of parameters that you can tweak. And that means that it's usually easier to optimize the efficiency of such simple systems. And so then you can put a lot of them in parallel and have something which has a somewhat large power output, but which is also very efficient. And one device which is ubiquitous in this kind of literature about quantum thermoelectricity are quantum dots. These are nanoscale devices which trap electrons in all three directions of space. And when you specially confine electrons, they will arrange themselves they will spread on quantized energy levels. And what that means is basically for an electron to be allowed to cross a quantum dot, it needs to have a certain precise energy given by this quantization condition here. So here I give two examples of the kind of thermoelectric systems that have been designed. Here you have an energy harvester where you have two coupled, capacitively coupled quantum dots, and where the heat is extracted from this reservoir H here to drive a heat current against a potential bias across the second dot here. And down here you have a refrigerator which makes use of the physics of quantum dots. And so one of the very interesting aspects of quantum dots for thermoelectricity is the simplicity of their transmission probabilities. And transmission, like energy filtering and transmission of electrons at certain energies, is really a key feature for thermoelectricity. So I hope I can convince you of that with this simple kind of picture. So imagine here that you have a very schematic, sketchy representation of a thermoelectric. So on the left, you have a hot electron reservoir. So some electrons are excited. And on the right, you have a colder one, but with a higher chemical potential. So it's a voltage bias, basically. And the gray bar in the middle basically represents the fact that the thermoelectric system that you have connecting those two reservoirs might block electrons from crossing at certain energies, or might allow others to pass. And you basically understand that if you choose these energy filtering properties appropriately, you can, for example, block all the flow of cold electrons from right to left. So if you block everything below the chemical potential of the right reservoir, and then only the electrons in the left reservoir, which have been thermally excited, will be able to cross. So that will give rise to an electric current from left to right. And this electric current is accompanied by a heat current, because those electrons are electrons with a rather high energy, and so they carry some heat with them. So now, how to translate that mathematically? Throughout this lecture, we'll mainly use the Landauer-Büttiker formalism, and this formalism relates the scattering properties of your thermoelectric device to its thermoelectric properties. The basic idea is that you represent your system as a central scattering region connected to two idealized electron leads. And you assume that you can derive by other means a transmission function for this central scattering region, which means that you can tell that if an electron arrives on this region with a certain energy, it will have a certain probability to be transmitted or reflected into the same lead. And when you do the calculation, what happens? Well, you realize that now that the electric current, for example, through the device can be calculated by taking the integral over all energies of the product of the transmission function of the device, T, and the difference of Fermi functions on the left and on the right. And similarly, you can calculate all sorts of currents. Here I give the example of the heat current out of the left reservoir. And you have the same type of integral, except that you have to add this additional energy factor here, which measures the heat carried by electrons at certain energies. And so now, if you, it already shows you that understanding these transmission functions is a key ingredient of thermoelectricity. And so what's usually done is that people are usually interested in the linear response regime, where the voltage bias and the temperature bias across the thermoelectric device are small enough so that you can expand everything to first order in those biases. And so in that case, you will see appear all these usual transport coefficients. So here in these formulas down here, G is the electrical conductance, S is the Seebeck coefficient, pi is the Peltier coefficient, and C is the thermal conductance. And now if you relate these formulas with the one above here, you understand that you will be able to calculate all of these transport coefficients just by, as long as you know the transmission function for this device. And so then once you have derived all of this, it is quite straightforward to infer the power and the efficiency of your device. And so the bottom line here is really that once you know the transmission properties of a device, then you can perform the full thermodynamical analysis of this thermoelectric system. So what does that become for quantum dots? So as I said, you have quantized energy levels for quantum dots. And so if you focus on transport around one of these quantized energy levels, it is usually assumed that the transmission function will have this Lorentzian shape centered at the resonant energy of the dot, so which is denoted by ED here. And the width of this transmission function, gamma, is related to the coupling of the dot to the electron reservoirs on the left and on the right. And so hereafter, I will be focusing on the case of single-level quantum dots. And that means that those are systems for which you don't have Lorentzian resonances on top of one another. It means that you must assume that the level width for each level is much smaller than the level spacing for different the different quantized energy levels. So that already assumes a kind of a weak coupling assumption. And furthermore, the Landauer-Büttiker formalism is applicable only when there is no interactions within the scattering system, so the dot here. And so we must assume that the system is small enough so that Coulomb repulsion will prevent the dot from being doubly occupied by electrons. So we assume that electrons will cross the dot one by one at an energy very close to the resonant energy of the dot. So if you want to go all the way down with coupling assumption, when this weak coupling, this line width here is much smaller than the thermal energy, you realize that this transmission function up here becomes infinitely narrow around the Lorentzian, the resonant energy of the dot, so that you can assume that only electrons whose energy is exactly the resonant energy of the dot will be allowed to cross. And that regime is very interesting because then it simplifies a lot all your formulas, and especially the electron current through the dot is just given by the coupling times the difference of the Fermi functions on each side. And additionally, since all electrons that go through the dot have the same energy, you can calculate the energy current very easily by just multiplying this electron current by the energy of each electron. So that's what is called the tight coupling of the energy and particle currents, and that will be very useful for thermodynamical analysis.
Etienne, typically you would include the electron charge in these latter formulas.
Yeah, yeah, probably I've been a little bit, it might be a little bit confusing here because, as you said, here I have included the electron charge. So this is the electric current. And here, I should have precise here, but this small j here is actually just the particle current down here. So yeah, maybe I should have formulated everything in terms of the same current. But of course, yeah, if you are interested in the electric current here, you have to multiply this by the electron charge. Yeah, I'm sorry if that leads to more confusions. So now let me present some works we've been doing in the group recently with this resonant tunneling physics. So the starting point of our ideas was this kind of geometry, which had been introduced by Professor Jordan in a paper from 2013. And in this paper, the idea was to have an electronic cavity here in the middle, which is heated up from the outside. You imagine, so you have an outside heat reservoir, which just gives some heat to the cavity to maintain its temperature constant and quite high. And this cavity is coupled by electron reservoirs at lower temperatures through resonant tunneling quantum dots. And so now if you have a voltage bias, let's say, for example, the reservoir on the right has a higher chemical potential, you want to use the heat which is absorbed by electrons when they go into the cavity to overcome this voltage bias, and so generate electrical power as a result of the heat which is absorbed here. And one interesting aspect of the system is that since electrons which enter from the left or exit to the right must do so at prescribed energies, it is quite simple to tune the power output or the amount of heat you extract by appropriately positioning the dot resonant energies. And I want to point out that this kind of system has been experimentally realized recently. So with this kind of system here, you have the dots on the left, the dot on the right, and the cavity in the middle. And they've been able to predict with a nice precision the power output of such an energy harvester. And the question we asked is either is it possible to realize an absorption refrigerator with the same kind of geometry here? So if you were there last week and followed Bibek's talk, you must remember what an absorption refrigerator is. Basically, the idea is that instead of generating electrical power, we are using heat from the cavity to drive a heat current from a very cold reservoir on the left to a less cold one on the right. And so in this situation, we must assume the following hierarchy of temperatures, where TH is the highest temperature and TL is the coldest temperature. And we want refrigeration to be driven uniquely as a result of heat which is absorbed in the cavity. And so we must ensure that there is no additional voltage bias between the reservoirs, so we set everything at 0. But the story is quite different for the chemical potential of the cavity, because as I said, the cavity receives some heat from the outside, but it only exchanges electrons with reservoirs L and R. And so in the steady state, you cannot have an accumulation of electrons within the cavity. So you must ensure that whatever enters from the left exits to the right. And so that will constrain your chemical potential, and you will have to solve this kind of particle conservation equation here to determine the chemical potential. So once again, when I have small j's here, I'm referring to particle current, so the number of electrons entering the cavity per unit time. And so if it was quite straightforward to understand how absorbing heat in a cavity can allow you to generate electrical power, I think it's a little bit more subtle to understand how this can help you achieve refrigeration here. And actually, there are two possible processes. So let me describe the first one here on the top panel. So the idea to refrigerate the cold reservoir here is to remove as much electrons above the Fermi level as we can. So the idea is that you will position the first dot just above the chemical potential here. So you have some hot electrons here that will be able to enter the cavity. And now within the cavity, they are excited, they acquire some energy. And you need to position the second dot high enough so that you have enough free space, basically, in the right reservoir, which is a little bit hotter, so which has more excited electrons here, to allow them to cross to the right reservoir and ensure that you will have a steady heat electric current from left to right. And so in that first situation here, you see that both the electron flow and the heat flow goes from left to right. In the second situation here at the bottom, we will have heat transfer via cold electrons. So the situation is quite different. Instead of removing hot electrons from the left, we wish to put cold electrons on the left. So what we do is that we have to position the right dot energy low enough so that we can remove cold electrons. So we have a lot of cold electrons that we can remove in the right reservoir. Once they enter the cavity, these electrons must be excited because we have to position the left dot energy somewhat close to the chemical potential to make sure that there is enough space available so that you can add these cold electrons within the left reservoir to cool it down. And so that's how we use the heat from the cavity to power this refrigeration process. And in this last case, it's interesting to see that even though the heat still flows from left to right, electrons flow in the opposite direction. And so those two possibilities for refrigeration are actually an illustration of the electron hole symmetry within the system, because you can formulate this second scenario here as a way to transfer hot holes from left to right, basically. So now I'm going to show you some of the calculation we have to do. So we assume weak coupling. So in this case, we have an infinitely sharp transmission functions, and electrons will only cross precisely at the dot resonant energies. So that will enable us to simplify greatly the electron current written down here. And as I have emphasized previously, we have to equate the current coming from the left and the current exiting to the right. And the way to equate that is to solve this equation for the chemical potential mu H. And so this is something which is doable analytically. And once you do that, you just put the solution back in one of these formulas and you obtain the left-right particle current through the cavity. And since we are in this weak coupling regime, if you remember, in that case, the energy and the heat currents could be very easily inferred from the particle current, because you just have to multiply this particle current by the energy that all these electrons carry. So the cooling power, which is the amount of heat you remove from this left cold reservoir here, is just this particle current multiplied by the energy of the left dot. And the resource you are using to give rise to this cooling power is the heat that is absorbed from the cavity. So here you have to consider the energy balance across this cavity. So you have some heat incoming from the outside, Q dot H, and you see that in the steady state, heat does not accumulate into the cavity, so it must equate the heat which is carried by the electrons crossing through the cavity. And so you realize that in the steady state, this heat current that is going into the cavity is just J times the difference of dot energies across the cavity, which we call the energy gain. And one thing which is really interesting with these these formulas is that now if you calculate the coefficient of performance, the particle current cancels out, and you have a very simple formula for your coefficient of performance, which only depends on the position of the dot energies. So you understand that appropriately positioning those dot energies will be crucial to optimize the performance of this refrigerator. So now let me just discuss a little bit the laws of thermodynamics for this device, because of course we still have to make.
Can I ask a question before you go
on? Sure, go
back
ahead.
On I guess here you set the chemical potentials of the left reservoir to be 0. Is that right?
Yeah, exactly. Yeah. So maybe I haven't emphasized that enough. But all energies will be measured with respect to the left reservoir chemical potential. And that will be very useful in the future, because it just tells us that whenever energy is positive, we are transporting hot electrons, and whenever energy is negative, we are basically transferring cold electrons. So that's a really neat way of discriminating these two, differentiating these two situations. Yeah, so we have to also ensure that.
Etienne, I have a question. If
sure.
I may. On this slide, Q dot H.
Yes.
You have expression for it. How close it to the real situation? I mean, it is rather strong assumption that Q dot H is equal just to what you have written. There may be parasitic processes in reality which will spoil the situation. What about, is there any justification for this expression?
Yeah, so if I remember correctly, for example, this estimation of the Q dot H was a real technical challenge for the experimental applications of this device. So now, I guess the assumption is just that the cavity is rather well isolated from the outside environment, and that so that it only exchanges heat with a single heat source and with the other electron reservoirs. What we assume usually is that so the parasitic processes that can happen within the cavity, such as electron-phonon interactions or electron-electron interactions, will actually serve as a way to have the electrons entering the cavity quickly thermalized. So I think, I hope I'm answering your question correctly, but probably
you are addressing yes. But if you will do such insulation, how about transmission function? Because you still need to have a good transmission, right?
Yeah.
To the right.
Yeah. So from what I remember, in the experimental design of such system, they are basically building the dot and the cavity on the same substrate to ensure that they are well coupled, while all the rest is isolated. So they are building basically everything on the same gallium arsenide substrate, and yeah, so they really have this 2D electron gas in the middle of the cavity, and you just have some little gates here that will separate the dots from the cavity, but everything else they are really built on the same chip here.
Yeah, so I guess I can add to that and just say that usually the main heat transport mechanism in bulk material, for example, would be phonon mediated heat transport, right? And so here we're neglecting the phonons in this model, but then there are certain regimes where you can justify that. I think Étienne's talking about some cases where you can do that, where you have neglect the direct phonon transport.
And typical temperatures, that means probably that temperature should be relatively low, right? Already relatively low.
Exactly, yeah. So these are cryogenic, yeah.
Yeah, interesting. Thank you. Thank you. I don't want to interrupt for too long. Thank you.
No problem. Thank you for the question. And so, yeah, about the laws of thermodynamics, the first law is basically automatically satisfied because basically we have assumed energy conservation throughout, so it's not really a challenge. But the second law gives you more information about the dot energies you have to consider and the temperatures. So when you put everything together, you obtain this big condition here. So it's the product of two terms. One of them is the current, obviously. And if you recall, we had two possibilities for the heat transfer. So either via hot electrons or via cold electrons, and that correspond to different signs for the electric current. And these different signs will mean different signs for the big parentheses here. So all in all, when you consider all that, we obtain some constraints on the dot energies and on the temperature. So here for the dot energies, we see that first of all, both of them need to have the same sign. So if you recall Professor Jordan's question, it means that they will be on the same side of the chemical potential, and their ratio must be smaller than some ratio that we call the stopping ratio. And the physical interpretation behind that is basically that if the right dot energy is too high, then it's not possible for the cavity to excite electrons to such a high energy and enable them to exit to the right. And similarly, you have a constraint on temperature, so the right reservoir temperature cannot be too big, otherwise it's not possible to excite electrons to an energy high enough. So let me show you briefly some results here. So on the top panel, you have the cooling power as a function of the energy ratio. And we have some nice parabolas here. In reality, it's not exactly parabolas, but you have to be at fairly high temperature to start to notice some asymmetries and more complicated effects. So the bottom line here is that usually you have the highest cooling power when you position the dot energies exactly at the middle of this allowed range. And on the bottom panel here, you have the coefficient of performance as a function of this energy ratio. And I remind you that this coefficient of performance only depends on dot energies, so it's independent of temperature. One thing which is interesting to note is that when you are at the stopping energy ratio here, it corresponds to the Carnot coefficient of performance for the corresponding temperature. So this is something which is very usual in thermoelectric system, that when you reach these kind of stopping temperatures where you have no power, no power output, you are actually in a thermodynamic reversible situation where the efficiency is maximum. And finally, I want to draw your attention on the red curve here, because you notice that this curve corresponds to the case where both reservoirs have the same temperature. So it corresponds to heat rectification, where basically by just positioning the dot energies with respect to one another, we're able to dictate the direction of the heat current. And so this gave us an additional idea, which is what happens if we can put a lot of these absorption refrigerator in series, and can we drive some heat current all across this long chain? So here we consider this new situation where instead of having a single cavity in the middle, we actually have a whole chain. and we have put alternating temperature because we know that we will be able a priori to drive a heat current through each cavity. And as before, we assume that all of these cavities are heated up from the outside by some outside heat sources. So you can imagine, for example, that you have some kind of quantum computing platform and a lot of systems undergoing irreversible computation processes. So they are dissipating a lot of heat. And now we propose to use this heat to perform some additional thermal management processes throughout the system. But if you remember, one of the key point of our previous system was to derive the chemical potential for the cavity. But now that we have a lot of them, we have actually to determine the chemical potentials for all of these cavities. So we have this very complicated system of equation to solve with all this, where all these currents involve Fermi factors. So it's a highly nonlinear system, which is not possible to solve in the general case. So we had to resort to linearize all the Fermi factors in here, which is an approximation which is valid when the first argument here, so this difference between the energy and the chemical potential of the neighboring regions, is much smaller than the thermal energy. In that case, the system becomes linear and can actually be solved analytically. And here's the result we obtained for the electron current across the whole chain. And you see that it takes a somewhat simple form. We just have this prefactor here, and the other factor is just a sum of all the energy differences across hot cavities.
A brief question, Etienne, brief
yes,
question.
Sure.
Is this excitation, my initial impression was that it should be resonance, and now you are not considering resonant excitation in the cavity, or I'm missing something. I mean, these arrows, red arrows which you have, are they resonant source or non-resonant?
No, non-resonant source.
Non-resonant.
Probably I haven't emphasized that enough, but cavities are really much bigger than quantum dots. So we call them cavities, but they contain a large number of electrons. They are very different from quantum dots. Basically, you don't have the importance of resonant energy levels is different here. So you really have to differentiate cavities from dots, which are coupling cavities to the reservoir.
Okay, thank you. Thank you.
Yes, so the red arrows just indicate that there is a source of energy that keeps the temperature constant in these electron reservoirs.
And basically, we have to assume that there are some inelastic processes taking place in the cavity, so that electrons which enter the cavity relax quite quickly, so that we can assume that we have an equilibrium Fermi distribution within the cavity, each cavity basically.
So that if you will consider in the left EL and ER, these levels are distributed very close to each other, so that you can get non-resonant excitation working here.
So basically, EL is the energy level for the quantum dot, which is coupled to the left of the cavity. And electrons will arrive into the cavity at this precise energy EL. And normally, since those cavities are not really reservoirs of electrons, this should mean that their distribution within the cavity has some non-equilibrium component to it, right? But then we assume that these electrons that will enter the cavity at this precise energy EL will quickly thermalize within the cavity because of all the interactions which are taking place, such that we assume that they there really is like a nice Fermi distribution within the cavity, and similar for ER.
So and they are relaxing because of which mechanism? Because of phonons or
phonons and also electron interactions.
Okay.
So we imagine basically that the state in the cavity would be some kind of Landauer Fermi liquid, right? Where you can have what is important is that we can have a way for our theory to work. What is important is that we have a way to somehow link electrons to a single particle state. So to have a rather simple many-body state with a nice Fermi functions and a defined energy basically for each electron.
And at the same time, it is isolated pretty good from the environment, as you said.
Yes, basically. That's the idea.
Okay, thank you.
And so, yeah, so once you have derived this electron current, since we are still in this very simple resonant tunneling formalism, the heat currents all across the cavity can be determined all very easily by just multiplying by the appropriate energy difference. And so you can think that this is the end of the story, basically, that now you have determined all currents throughout this chain. And so you have fully characterized the thermoelectric behavior of this chain. But we decided to go a step further and actually to turn the perspective around. And now we ask a different question, which is now instead of having a given chain and deducing the heat currents through the chain, what if instead of that, you give me the heat currents, and now I will tell you how you can position the dot energies to realize the heat current distribution that you have chosen. That's what we call thermal control. And you can think about it as some kind of advanced air conditioning system. So imagine you are with all your colleagues in neighboring offices, but everybody has different opinions as of if they want heat or AC. And so instead of having everyone undergo the same thing, you would be able to tweak some little things in the whole network so that everybody is happy with the heat they receive. And so to mathematically formalize that, we start from the expression for the heat currents, which we have derived, as I have explained previously. And now you need to consider these heat currents not as results, but as your input, and your output will be the dot energies here. So basically, what I'm trying to say is that you have to solve these equations, this big system of equations, with the heat currents as inputs, and you have to solve it for the dot resonant energies. So you have to find the dot resonant energies that will satisfy these equations. Here it's a little bit tricky because, as you can see, it's some kind of quadratic system, but it's still solvable. So here is the result down here. So since it's quadratic, you have two solutions, which correspond to the plus and minus signs here. And that's also a consequence of electron hole symmetry, those two solutions. And now it can be a little bit impressive at first, but apart from this big prefactor, the last term here is really just the sum of all heat currents which are to the left of the dot you are considering. So now let me show you a couple of examples of what we can achieve with that kind of solution. So here we have a very simple system where you have only 3 cavities coupled together, and you're in a situation where you extract heat from the left, and this heat extraction, this refrigeration is powered by, or rectification maybe is powered by absorbing heat from the first hot cavity. And now let's say you want to swap the heat currents for the H1 and H2. You want to absorb heat from the second cavity here. And our solution shows that you just have to shift both energy, the inner dot levels down by the same amount. And nothing else will change in the chain, except the fact that now the heat is absorbed from H2. And another interesting thing about this particular situation is the fact that you see that even though H2 is not directly connected to this left reservoir here, since everything is coupled together as a result of particle conservation, you are still able to power this rectification process here by extracting heat from a cavity which can be far in the chain. Now, something rather different when the case where you have a large number of cavities. So here you have 100 hot cavities coupled with 99 cold cavities. And the red line here basically shows the heat distribution.
It's slowly loading, Etienne. Why don't you wait for a second while I think the picture is loading.
Oh, okay, sorry about that.
Maybe I can ask a question while it's loading. I guess one thing we think about that is that in the first instance, you have that energy gap around the first cavity, whereas in the second solution, you have the energy gap around the last cavity. That's another way of saying I'm pulling heat from one or the other, depending on where the jump in the quantum dot energy levels is.
Yeah, exactly. I think the bottom line the thing to realize with this kind of system is that it's really the energy differences which will dictate in which way current will flow. And so, as you said, depending on where you put the energy difference, you can have heat current in one cavity or the other. Can you?
We're seeing your slide now. Yeah, go ahead.
Okay, very good. So,
can you please explain what means numerics and prescription?
Yes, I will. So basically, the red curve is just the fact that just the distribution that we choose. So this is my input. I say I want this distribution. But now, if you remember correctly, we have made some approximations to end up to our thermal control solution. The main one was that we linearize the Fermi factor. So what I did here is that I used our prescription, so our result, and I put that in the exact equations for the heat current. So solving everything for the chemical potential numerically, and I compared those results to what we want to achieve. And so in that case, it's clear that we have a very good agreement. But as I said, it's not perfect because we did this linear approximation. And so it's not clear actually to know when you give me a certain heat current distribution, whether the linearization of the Fermi factors will be valid or not once we have performed this whole solution. And we have identified some hand-waving criteria for the solution to give accurate results. And so they basically concern three quantities for your heat distribution. The first one is the average value, the average heat you extract, basically, the magnitude of the heat currents which are in the picture. The second one is the asymmetry between hot and cold cavities. You really want them to compensate one another so that you don't have to have really big energy differences between two consecutive dots. Basically, that's the idea. And the last one is about dispersion of this heat current distribution. But it's a less important, this condition is less important because the bound on the average value and the asymmetry is really tighter. And so it means that our scheme will be particularly sensitive to those parameters. And so, and one last point is that outside of this regime, thermal control can still be achieved, but it's in a weaker sense, which we call relative thermal control here. So maybe in a few minutes, I'd like to go through the last part of my talk very quickly. So, so far, I've only been discussing some simplified pictures where you have weak coupling to the reservoir, so that allows you to make all sorts of simplification. But actually, when some people, you might expect, actually, since you see the formula for the current are all proportional to this coupling to the reservoir. So you see that it seems that the power output of your machine will then be bigger if you take a strong coupling, right? And so I'd like to discuss that briefly. So that's some work I did some years ago, where we consider an exactly solvable model, which is called the Fano-Anderson model, where you just have a discrete level, which is coupled to idealized free particle reservoirs, and there is some hopping term between these reservoirs. And this model has been introduced in the early 60s, and it's exactly solvable, which is very interesting as a benchmark for open systems. And what I want here is to study its transmission properties. And one point that I want to emphasize here is that on top of considering strong coupling, or basically any coupling possible, we consider that in the reservoirs, the spectral density, which is given by this formula here, but you can just imagine that as basically the product of the coupling amplitude and the density of state in the reservoir. So we assume that the spectral density is not flat. So it varies with energy, and in particular, there can be regions, the band gaps, where it vanishes, it's zero. And what we realize is that in these band gaps where the spectral density vanish, you can have at high coupling what we call bound states. So those their energy omega b must satisfy these two conditions. And these bound states can be interpreted as basically the discrete energy level of the single level quantum dot, which is lambda shifted. So lambda here is the lambda shift as a result of level repulsion, and that will give rise, when the coupling is high enough, to an eigenstate of the full system outside of this continuum. And so what's interesting with this model is that the lambda shift can have an exact formula here. It's given by the principal value integral of the spectral density. What you realize is that if your spectral density is flat, it just cancels, it's just zero. So this lambda shift physics cannot be understood if you consider something which doesn't have a band structure. And so with this model, as I said, it was exactly solvable. So we have been able to find an exact formula for the current, which takes this form, this Landauer form. And now we have this exact expression for the transmission function. It is quite reminiscent, actually, of the usual expression, but now the width and the resonant energy all bear some energy dependence, which make everything more complicated. But I want to draw your attention to this factor here, so the resonance. And you see that when omega cancels here, so when you solve this equation here, you have perfect transmission, unit transmission. So that's what we call the states at this energy perfectly transmitting state. And if you realize that these states have this condition here is quite similar to that one. So there is some non-trivial relation to bound states here that we want to emphasize. The difference is that perfectly transmitting states are inside the continuum, while bound states are in band gaps. And so let's just give me an example of this kind of physics. Here we consider a case where the spectral density grows like a power law. So you have this parameter K, which is basically the intensity of the coupling. And the spectral density grows with the power law S. S is like sometimes called the omicity parameter. It's basically something that can happen at the band edge of semiconductors. In this situation, we find the following kind of phase diagram. You either have no bound state or one bound state. In the red zone, you have one bound state, and the horizontal axis here is the coupling parameter, and the vertical axis is the spectral exponent. You see that if you increase the coupling, you are from a situation without a bound state to a situation with a bound state. And we want to study, to understand what this kind of transition means in terms of transport properties. So here is a transmission function for various value of the coupling. So the bluish lines are for low coupling, and the orangey lines are for higher values of the coupling. So the dark blue line is for very weak coupling. In that case, you see, you really have something that resembles a Lorentzian resonance. But as you increase the coupling, the Lorentzian resonance starts to lose its shape, and the peak drifts towards the bound edge at zero energy here, and start to broaden. And when you reach critical coupling, that's the black line here, the perfectly transmitting state sits exactly at the band edge. And then if you increase the coupling even more, you have something completely different, some kind of rather flat transmission. So it really seems here that we have this perfectly transmitted state that becomes a bound state. And of course, this dramatically changes the transmission function. So you would hope that this has a dramatic effect on thermoelectric transport. So here are the various transport coefficients of the electrical conductance, the thermal conductance, and the Seebeck coefficient. And the dashed line represent critical coupling. And you see that you have very strong variations around this critical coupling here. And so now let me, yeah, can you see the slide?
It's loading. I think we're about out of time here. Just maybe another minute or two left.
Yeah, that's my last slide.
Okay.
So, but basically, yeah, let me just describe it, and then hopefully you will see it soon enough. So on this slide, I will show you, you will have some lasso curves. The vertical axis correspond to the efficiency of the thermoelectric device, and the horizontal axis, sorry, is the power output. And so you should see at some point these lasso curves, which represent all the possible realization of a thermal machine at a given coupling. And so can you see the plot now, or?
Not quite. Getting there.
You can try maybe reloading the slide.
No, just let it be. It'll gradually show up.
Yeah. But yeah, so basically what you should see in a while, let's say, is that the efficiency of the thermoelectric is not much affected by the variation of coupling. You don't have a very large reduction of efficiency, but that the power output is very much dependent on coupling, and especially you can have a much larger power output close to critical coupling, which means that it seems that it's kind of a sweet spot for thermoelectric transport, since you have a much larger power output without noticeable reduction of efficiency. And one other thing that you should see once it loads is that stronger coupling does not necessarily mean larger power output, because when you're above this critical coupling, then the power output simply drops, and so you really have to be careful about that.
Okay, we can see it now, Etienne.
Oh, okay, great. So yeah, what I was saying is that if you see the vertical axis, this is the efficiency of the device. And now you see that there is, for various couplings, it does not vary that much, the maximum efficiency of the device, but the power output is much bigger for this black lasso curve here, which corresponds to critical coupling. So that's why I say it's a sweet spot for thermoelectric transport. And yeah, the other thing is that for these orange lines, which represent very high coupling, you don't have a much larger power output, which means that basically more power does not always mean more coupling. Sorry, stronger coupling does not always mean more power. Is more subtle than that. And so yeah, I leave you with the conclusions here. And if you have additional questions, I will be happy to answer. Thank you for your attention.
Okay, thank you, Etienne. Very nice. We already had several questions during the talk, but any more that we'd like to ask?
Maybe if you can say a few words more about experimental attempts to demonstrate these effects. You said something, but very sketchy at the beginning.
Yes. Let me go back.
How many groups worldwide are trying this method?
As far as I know, only one. Yes, because so let me just.
Well, but maybe more broadly, not this particular resonant tunneling one, but how many people are in mesoscopic thermoelectrics?
Oh, yeah. Too many people to be counted, I guess.
No, quantum dot related thermoelectrics.
Yeah, so the groups I'm more familiar with are the group of Lawrence Molenkamp here in, so I think he is in Germany somewhere. So that's his group here. This is the group at the University of Cambridge who are doing this kind of quantum dot thermoelectrics here. So they did that refrigerator, and they are also the ones who designed this this realization of this theoretical proposal by Professor Jordan and collaborators. And then I think you have many groups in Grenoble, for example. I know that in Grenoble, where I did my PhD, people are mainly they were not really interested maybe let's say thermoelectric devices per se, but they are doing a lot of things with quantum dots. Notably, they were designing what they call an electron turnstile, where they can move a dot energy level up and down so as to extract, I think, electrons one by one. That was a big thing when I was there. I don't know where they're at with that now. And yeah, those are some notable people I'm aware of.
Yeah, Christian Gladley's group is another group in Paris that does this kind of experiment. There may be six or seven groups working on this kind of stuff.
Andrew, why I was asking this question, because quite a couple of days ago, there was a dear colleague's letter from NSF encouraging to think about cryogenic coolers for quantum computing applications in sub-Kelvin region.
Exactly. Yeah. Armin. Yeah, I had a friend of mine email me, say, Andrew, we should submit something to this. So yeah, I'm aware.
Yeah, very good, because we can do that in the lab. I mean, having machines, we can manufacture these quantum dots and try some cavities or whatever else is required. So this is something very interesting.
Okay, yeah, let's talk, Armin. Let's talk.
Okay, good. Yeah, thank you, Etienne. It was very interesting, very interesting.
Yeah, thank you for your questions.
Yeah. Other questions from the Zoom folks? Anyone? Any other questions here? Oh yes, okay, to target.
Etienne, can you go to slide 14?
14, yes.
Yeah, about these two inequalities, I was just trying to understand what the difference is, because
at the bottom?
Yeah, are there like two ways to look at the same inequality, or?
Yeah, basically you're right. So it depends on whether you assume that you have control over the position of dot energies, or if you have control on temperatures, basically. So in the first inequality here, you assume that basically temperature are constants, and the only thing that you can control are dot energies. So you need to see what are the regimes, what are the possible values for dot energies, basically that will satisfy the second law, and that will give rise to absorption refrigerator. And on the last one here, it's the opposite. You assume that maybe your dot energies are fixed, but now maybe you can vary the energy of the temperature of the right reservoir. And you see that if you assume fixed dot energies, you have a range of temperatures which are allowed for your right reservoir. So yeah, it's two ways of looking at the same thing, I would say. Exactly.
Thank you.
Okay, I think we're out of time. So let's thank Etienne again for this well-prepared talk. It's very good.
Thank you very much.
Thank you. Bye-bye.
Bye.